Gentlemen, welcome back. You clicked on the thumbnail. You know what we're talking about, or you don't, and that's why you clicked on the thumbnail. Welcome aboard. The little blue switch, ERMS, maintenance mode, RELT, ARMS, tons of names. They all do the same thing, more or less, but they do it in slightly different ways. If you're a tech looking for requirements, testing procedures, skip to the timestamp here. If you have no idea what I'm talking about, we're going to spend the next couple minutes getting you familiar with maintenance mode, what it does, why we have it, and what its limitations are. Each manufacturer of switchgear and large power circuit breakers has their own name for it. So let's get that out of the way first. A generic term you might hear is energy reduction mode switch or energy reduction mode system, ERMS for short. Square D uses this nomenclature sometimes. Eaton calls it arc flash reduction mode system, or ARMS mode for short. On GE or ABB systems, it's called reduced energy let through, or RELT for short, RELT. To get you caught up, ABB bought GE's industrial power product lines and effectively just rebranded a bunch of stuff, rebranded all GE's breakers. But there's also separate ABB product lines that are made in Italy. It's kind of hard to follow, but as far as I'm aware, they all call their maintenance mode system RELT. Siemens Dynamic Arc Flash Century, probably the worst name, but works roughly the same. Regardless of the brand, maintenance mode systems are used to lower the incident energy or the energy of a potential arc flash during a fault. When you turn that little blue switch on the front of the switchgear, the protection settings in a circuit breaker change and lower the amount of time or current required to cause the breaker to trip. This can, when used correctly, make the power distribution equipment safer to work on while it's energized. Note that I said safer. It's never safe to perform energized work, but this is a step in the right direction. If you're not trained, competent, qualified, and authorized to work on energized electrical equipment, you're much safer assuming there's a fire-breathing dragon in the switchgear that will melt your face when you open the electrical cabinet. For clarity, I'm going to call them all maintenance mode for the rest of the video unless I'm referring to a very specific brand. Why does it exist? Well, they exist for two main reasons. First, the law, because time has proven companies wouldn't give a shit about their employees unless they were legally required to. The NEC requires new installations of 480 volts, 1200 amps or more to be fitted with some sort of protection designed to limit arc fault energy. A maintenance mode system is just one of the options for this. I can make a whole video about all of these. Let me know down in the comments if you're interested in any of those. Without getting too far in the weeds, if a power system is nominally rated 1200 amps or higher and the instantaneous rating of the breaker can't be set below the system's arcing current, one of these methods needs to be implemented. A bit of a tangent, the arcing current here is referencing a calculated theoretical value of fault current which the system would need to maintain in order for an arc to be self-sustaining and thus dangerous in the event of an arc flash. I'm no engineer, so take this with a grain of salt, but the arcing fault current is typically like 40% of the bolted fault current and depends heavily on the impedance of a system and the size of a transformer that feeds it. This rule only applies to residential and commercial. Utility and industrial applications don't have to worry about meeting the NEC 240.87 requirement. However, maintenance mode and some of these other methods can make it a lot easier to stay in compliance with other OSHA or NFPA requirements. Secondly, nearly all breaker trip settings, long time, instantaneous, short time, ground fault, under voltage, whatever, they're all designed and coordinated to protect the expensive power equipment or keeping the cabling in the walls from overheating and catching fire. Coordination study engineers need to allow for extremely high currents to flow for short periods of times for things like motor inrush so that the system works and doesn't trip every time a large load is energized. That wouldn't work. This leads to huge potential current and extremely dangerous levels of energy that can be released in the event of an arc flash. Maintenance mode is one of very few systems that sole purpose is decreasing the danger to people working on or near the switchgear. If you've been through NFPA 70E training, you'll know that the upper limit of what PPE can reasonably protect you from in an arc flash is about 40 calories per square centimeter. By enabling maintenance mode switch, the incident energy of a system can be lowered dramatically, in some cases from well over 40 cal to something more survivable like 10. Some use cases for this are opening or racking out breakers, performing IR scans or visual inspections, replacing buckets in energized MCCs, or opening panels downstream. Anytime a worker is at an elevated risk of arc flash, it's a good time to enable maintenance mode if you have it. It's important to note that the PPE required isn't affected unless you have a specific procedure or arc flash study data stating what the energy levels and PPE required are with it enabled. Sometimes you'll see two arc flash stickers, one with maintenance mode on and one with it off. For the most part, to activate maintenance mode, you'll simply turn on the blue maintenance mode switch, which sends an input to the affected breaker. This is usually the main breaker on a switchboard, but can be multiple feeder circuits that activate all at once on large switchgear. You'll need to verify that the blue LED illuminates, and if you can, verify that the trip unit of the breaker you're enabling it goes into maintenance as well. Some trip units will make it easy and have a blue LED right on the front, like on this Eaton Digitrip 520MC, but I know on some Square D breakers, the MicroLogic 6.0 trip units, will only show it as a settings change that's nested really far down into the menus. Once enabled, they typically lower the instantaneous trip pickup. This can either be displayed as simply lowering the setting or by activating some other mode in the trip unit. Let's take the following breaker for example. Under normal conditions, for this 1200 amp breaker, the settings will be long times 1200 amps, 1200 amp frame rating, so with a 6-second delay. Short time is set to 5, which would be a 6,000 amp pickup with a 0.06 second delay. Instantaneous is set to 15, that's 18,000 amps. And then our RELT setting, our reduced energy let through maintenance mode setting, that's going to be 9, which is 10,800 amps. So with maintenance mode or RELT disabled, the instantaneous trip is 18,000 amps. It takes 18,000 amps to get that breaker to instantly trip. When enabled, maintenance mode turned on, it doesn't affect the long time or short time pickup or the delay, but it will trip instantaneously at 9 times the continuous rating, 10,800 amps. This setting can be even lower if need be. In some cases, like with GE's RELT system for the IntelliGuard trip units, the breaker's instantaneous clearing time is further reduced by some sort of proprietary black magic. It actually makes the breaker trip faster. Often these maintenance mode settings simply bring the instantaneous setting down to the minimum of 2 or 3 times the frame rating. For this breaker, that would be, 2400 amps. This can cause the system to be incorrectly coordinated. Certain high inrush loads may now trip the main instead of the corresponding feeder breakers. Obviously, that's unacceptable under normal load conditions or normal operating conditions, but it's a worthwhile risk if you're going to be face first in open, energized switchgear during an IR scan. That can be the difference between needing to change your pants and having a closed casket funeral after an arc flash. We need to have a strict understanding of what maintenance mode does and doesn't do. Number one, if the system isn't set up and commissioned correctly, it doesn't do anything. I've seen more than a few installations where a switchboard was shipped with all of the provisions for our maintenance mode system, even having the labeled maintenance mode switch on the front of the board, but the trip unit in the main breaker didn't have an input for the maintenance mode switch. In my opinion, that's worse than not having anything at all because you can give the worker a false sense of security. If you're commissioning a system like this, it's your responsibility to check with the engineer, make sure that the settings are suitable without a maintenance mode, and remove that switch and plug the hole if it's not used. Number two, it definitely doesn't make energized work safe. It does nothing for the shock risk. The system is still hot and any energized conductors will shock you and they will kill you. The breaker will take longer to trip than it takes your heart to become irreparably and fatally damaged. It's likely that the impedance of your greasy body is high enough that the breaker won't trip anyway, so you'll sit there and sizzle like a neglected hot dog on the roller at 7-Eleven. Maintenance mode only lowers the time it takes for the breaker to trip during an arcing fault, but there can still be an arc flash. This will still release a ton of energy, and there's still going to be a fireball brighter than the sun. It's smaller and extinguishes sooner, so it's safer, but it isn't safe. Lastly, and I think most importantly, it only changes the incident energy for one small portion of the circuit. It does not affect the entire power system at a facility. Let's look at a typical application where a 2000 amp main breaker of a service entrance switchboard is fitted with a maintenance mode. The incoming cables and the bus on the line side, or incoming side of that main breaker, is only protected by the fuses on the primary side of the transformer outside that's feeding into it. This area doesn't trip for hardly anything, and enabling maintenance mode makes absolutely no difference if you're going to do work on the line side of that breaker. An arc flash here will laugh emphatically at the maintenance mode switch as it melts and falls out of the front of the gear. It also doesn't affect anything too far downstream. The arc rating of, say, a lighting panel on the far side of a facility is mostly determined by the size of that little transformer that feeds it, not the upstream protection at the service entrance board. In our example here, maintenance mode is only reasonably effective for reducing the energy inside the service entrance switchgear on the load side or immediately near these feeder breakers that I've got highlighted. Okay, so how does it actually work? Again, I'll have to generalize because it can be implemented in a million different ways, tailored to each installation for each type of breaker, for each switchboard. But for most installations I've seen, they work the same and they're all fairly simple. There's going to be a power supply in the switchgear, usually supplying 24 volts DC whenever the bus is energized. When the blue switch is turned on or placed into maintenance mode, it sends a 24 volt digital input into the breaker's trip unit. The trip unit then enables the new setting and closes a status contact, sending 24 volts back to the indicator light, telling you, the operator, that the system is actually in maintenance mode. You have to be careful with this because you can totally screw up the wiring, accidentally or maliciously, to make the light come on without having the breaker in maintenance mode. A system can be designed where multiple breakers are put into maintenance mode at the same time from one switch. For those, any indication feedback should be wired in series so that all of the breakers have to be enabled in maintenance mode for that LED to turn on. If you do it any other way, really you're doing it wrong, unless they're coming out of a communication module that sends the maintenance mode signal out to each breaker. We'll talk about those more in a second. For ABB trip units, RELT mode only works if the breaker is provided with a digital input module, like the signaling 2K module shown here. But it works effectively the same, except that the power supply is another expensive proprietary thing you got to physically plug into that breaker. Square D does it in two different ways. For their molded case power packed breakers, a maintenance mode switch sends a direct 24 volt signal to the trip unit and reduces the trip time using the same inputs that you'd use on the ZSI system. I'll make a video about ZSI at some point, I'm sure. Square D's other system, which they differentiate by calling it ERMS, does the same thing, except to get the signal to some of their micrologic trip units, there's an IFE communications module to send the signal to the trip unit over Modbus instead of a direct 24 volt input. I don't know why they do this, because 90% of the time it's a single maintenance mode switch for a single breaker. But I guess it makes it easier to add stuff to the system later or do monitoring, things like that. It only works on trip units that have this blue ERMS label on them. Since it's a communication function, you have to make sure that the trip unit is turned on and networked properly. A quick tip on those, if it looks like everything's wired up right, power's on, and you're getting the switch input to the IFE module, you have to hold down the T button on the IFE module for 5 seconds. It forces the IFE module to try to reconnect to the trip unit, and every time I've had an issue with it, hold the button down, it works fine. Siemens Smart DAS system is similar to Square D's ERMS system. Implementation requires a controller and a communications gateway, and they send the maintenance mode signal to the trip unit over Modbus instead of having a hardwired 24 volt digital input. It just adds complexity. You don't really know why they do that. They get to sell you more stuff, right? No matter what system you're working on, you can usually Google such and such trip unit maintenance mode, and you'll find the document that shows you how to set it up for your system, for your breakers. That's really the foolproof way to do it. All right, so how do we test it? Breaker testing is commonly required and is exceptionally important, but a lot of guys in the field lose sight of the fact that testing is sometimes the only safety net to catch broken, dangerous, or shitty equipment from getting turned on and killing somebody. Large power circuit breakers need to work. We prove that they work by using a high current test set and dumping a ton of current through them with a primary injection test set. We actually make the thing function how it will in the event of a fault. Similarly, if a facility is relying on maintenance mode system, we need to prove that works too. The team coming out to perform the breaker testing must fire up the maintenance mode system and verify that it works. Here's a couple ways to make sure that it's working during testing. If this is a bolt-in breaker that you're going to be testing in situ, I found the easiest way to do this is to take a small 24-volt wall adapter or like a laptop charger, and just lop the end off and use alligator clips to wire it right up to the output of the power supply. I've got one that I use. This is literally just an old laptop charger at 24 volts. I got this really nice long lead on that. You split them apart, get some alligator clips. It makes it really easy to clip right up to what you're working on. So once you've got it powered up, plug it in, turn it on, see what happens. Often this is going to turn on the display of the trip unit, if it has one, which makes it way easier to test anyway. With the maintenance mode switch off, primary inject all of the functions as you normally would, long time, short time, instantaneous ground fault. Then turn the maintenance mode switch on. If the breaker and system have maintenance mode indicators, like a blue LED or panel light, they need to come on. Square D and Siemens have some goofy contrived system that drive the status output from the trip units back to a communications module, whatever they need to be programmed. That process is unique to each trip unit, so refer to your specific O&M manual for that, but if it has it, it has to work. Now's a good time to check that the settings have been set. Often your coordination study will state what the maintenance mode settings are among all of the other settings. So those need to match. Now run the primary injection test again. Test it as exactly as you would for the instantaneous function, but at the maintenance mode value. So it should trip at the pickup for maintenance mode. If that works, just replace all the wiring as you found it, and when you're done measuring the board, obviously, ensure that you close in any control power disconnects and push in any fuses, and it's good to light up. That board's ready to be energized. After the board's been lit up, make sure that the indicators come on when you enable the maintenance mode switch to verify that the system runs on the internal power supplies and that you didn't, forget the fuses in your pocket. The process is very similar to draw breakers that you're going to test on a bench outside the gear. When you've got it stabbed up to your primary injection test set, use a small 24-volt power supply connected straight to the maintenance mode inputs on the breaker to enable it for testing. You'll need to determine what your benchmark is that the maintenance mode is actually on. Whether it's a little blue LED or it's a setting buried in the menu somewhere, note that as your report. During commissioning, once the breaker is in the gear and the bus is hot, it's your responsibility to verify that same benchmark. The maintenance mode comes on when the switch is toggled as the breaker sits in the gear. It needs to work under its own power in service. That's part of the test. The ABB EKIP is the only one I can think of where you can turn it on without an external power supply. So if you're bench testing it, it would be theoretically okay to enable it, to test it by enabling RELT through the EKIP Connect software, assuming you have the $500 USB adapter that they made you buy. Again, you haven't proven it works until you both trip the breaker at the maintenance mode setting and prove that you can turn on maintenance mode with the maintenance mode switch in the gear as it sits. If you don't do both, you're doing it wrong. Maintenance mode, ARMS, RELT, whatever you call it, whatever you have at your facility, it's a great idea. It's generally not too hard to implement, and it could genuinely save someone's life. It's imperative that you understand it, know what it actually affects and know its limitations, and most importantly, understand how it's implemented at your facility. If you have any questions, leave them down in the comments. I try to help everyone that I can, and if I can't, I generally point you to the resources that I would use if I was in your situation. Stay tuned for more videos just like this. I hope it was helpful, and I'll see you on the next one.